Alright, welcome back everybody. Continuing to work on our unit of radicals. Today we're going to look at how to simplify radicals and then multiply and divide them as well. Radical expressions for now. Later in the unit we'll look at some equations, but for now, how do we simplify, how do we multiply, how do we divide radical expressions? So before we get started with the note sheet here, I want to just give you a little heads up on where we're going. So let me go back to my scratch paper. So we looked at evaluating perfect roots. So for instance, and this is nothing you have to write down, again, this is just to help you understand where we're going with the notes. If I said, what's the square root of 100? We don't have an issue here because 100 is a perfect square. And the square root of 100 we know is 10, right? But what if I asked you for something like the square root of 50? Okay, the square root of 50 is not a perfect square. Now that doesn't mean that we can't do anything with it. It actually means we have two options of things we could do. So I can't give it an exact value, like I can't give it, like I can with 100, right? I can say 100 is exactly 10. I can't give it an exact value because it's not a perfect root. But I have two options. I could estimate it, and I could estimate it with a calculator, but hopefully this is something we could do without a calculator. Without a calculator, if you wanted to estimate the square root of 50, you'd be looking for something close to it that you know. So for example, I know that the square root of 49 is going to be 7, and I know that the square root of 64 is going to be 8, and since 50 is right in between 49 and 64, the decimal approximation for the square root of 50 has to be between 7 and 8. And because 50 is really close to 49, I would say that a good approximation would probably be something like 7.1. So we could say it's about 7.1. But unless we're dealing with like a real-world application, some kind of a word problem situation, we're not really going to want decimal approximations for answers because they're just not as accurate as our exact forms. Instead of estimating this with some decimal, which again could be done with a calculator, what we want to do is simplify it, put it into a simpler form. So to show you how to do that, I'm going to go back to our 100 for a second here. Hopefully you would agree that if I rewrote the 100 as 25 times 4, I still have the same value, right? 25 times 4 under the radical is still 100, so it's still the square root of 100. Now, is that still the same as, instead of 1 square root of 25 times 4, is it still the same as separately a square root of 25 and a square root of 4? Well, if you evaluate each of those square roots, the square root of 25 is 5, and the square root of 4 is 2, and 5 times 2 does in fact get us to that same answer we knew from the beginning, which is 10. Now the reason I show you this is because it's sort of what we're going to be using to simplify something like the square root of 50. So instead of looking at 50 as 50, we could look at 50 as 25 times 2. And as I just showed you with 100, the square root of 25 times 2 altogether is the same thing, is going to be equivalent to the square root of 25 times the square root of 2 separate, and that allows us to simplify at least part of this, right? The square root of 25 is 5, and the square root of 2 is going to be imperfect, which means it's going to stay. So the simplified form for this radical is going to be 5 radical 2. So 10 is our exact answer for the square root of 100, and 5 square root of 2, or 5 radical 2, would be the simplified form for radical 50. Okay, so the goal is to see what perfect squares are hiding in this radicand so that we can simplify at least that part of the radical. Okay, now it's really easy if you know your perfect squares and you're pretty good at breaking down a number in your head. So for instance, if I was looking at the square root of 200, it's really easy for me to say that 200 is the same as 2 times 100, where there's my perfect square. So the square root of the 100 would give me a 10, and that 2 would be stuck inside the radical. Or similarly, if I had a 300, I'm like, okay, square root of 300 is 3 times 100. Well, I could take the square root of 100 to give me 10, and I can't square root of 3, right? The issue is, what if you can't? What if you can't look at this number and see the perfect square that's in it? So maybe you're looking at 50 and you're not recognizing that's 25 times 2. Or maybe you're looking at 300 and you're not recognizing that's 3 times 100. Maybe you just can't see the perfect square that's hiding in that number. And sometimes I can't either. Sometimes the numbers aren't so maybe obvious. So what do we do if we can't tell what perfect square is hiding in that number? Is we use a factor tree. Okay, if I was to break down 50 with a factor tree, I'm going to divide it by 2 because it's even, and 2 goes in 25 times. And now I can see it. Now, let's say I didn't recognize it from there, because later on maybe you have to take this a little bit further. Any composite number we continue to break down. So 25 we would say is 5 times 5. Once the number is all broken down, what we're going to be looking for are pairs, because this pair of numbers represents a perfect square. So this pair of 5s represents 25, and because 25, or the square root of 25 is 5, this pair of 5s tells me that 1 5 can come out of that radical, and anything that's not paired up is going to have to stay inside of the radical. Okay? Let me show you how this works with a different example. So let's say we were trying to simplify something like, I don't know, the square root of, let's say 140, okay? If we were looking for the square root of 140, maybe we can't see the perfect square that's in there. Like maybe I can't rewrite that as 25 and 2 like I did with the 50. So the approach I would take is to use a factor tree. So 2 is going to go into this number, and I just started with 2 because it's even. 2 is going to go into the number 70 times, and then 70 is composite, so I can break that down again. It's still even, so I'm going to divide by 2 again, and 2 goes in 35 times. And then 35 isn't even, but I could still break that down to 5 times 7. Once I have it all broken down, again, what I'm looking for are pairs of numbers. So here's a pair of 2s. That pair of 2s there really represents 4. And what's the square root of 4? It's 2. So that pair of 2s tells me I have a 2 that can come out of the radical. And anything that's unpaired, like the 5 and the 7, is not a perfect square, is going to be stuck inside of the radical. So this simplifies into 2 and then radical 35. So the simplified answer, again, is 2 and then radical 35, or 2 square root of 35. All right, so you're going to break down your number, and you're going to look for pairs, because every pair represents a perfect square. A perfect square comes out of the radical. Anything that's not paired, not a perfect square, is going to have to stay inside of the radical. And like you saw here, if you have multiple numbers that are left over here, they're going to get multiplied. And similarly, if you had multiple pairs that came out, they would be multiplied as well. Now, when we get to the notes, we're not only going to be looking at square roots, we'd also be looking for cube roots, fourth roots, fifth roots to possibly be simplified. And the only thing that will change with those is the grouping. So it would take a number times itself, like 2 times 2, to make a perfect square. If it was a cube root, we'd have to have a 2 and a 2 and another 2 in our group for it to be a perfect cube. So our index of 2 here tells us to look for groups of 2. If we had an index of 3, we'd look for groups of 3, index of 4 would be groups of 4, and so on. And then just as another organizational tool here, when I broke down the 140, you saw me start with 2. And in general, when I'm breaking down a number, let me think of a good example here. Let's say I had like 92, okay? If I was to break down 192, as long as it's even, I'm going to use 2, and I'm going to do that as many times as possible. So 2 goes into this number, let's see, 96 times, and then that's still even, so I'm going to use 2 again. 2 goes in 48 times, and that's still even. 2 is going to go in 24 times, still even. 2 goes in 12 times, still even. 2 goes in 6 times, and then it's still even. 2 goes in 3 times. And the reason I use this approach is so that if I have a bunch of 2s that I'm ultimately trying to pair up, they're all lined up for me. So if I used 192, let's say, I don't know, 3 goes into it 64 times, and let's say I made that 8 times 8, or let's just so you can see the variation here. Let's say I went and made that, I don't know, 4 times 16, and then I have a 2 and a 2 here, and then I just end up with branches of things all over the place, and it sometimes makes circling my pairs kind of messy. So if you want to be a little more organized with your, it's not a requirement. You can really use whatever factors you want. But I like to use 2 as many times as I can. That way all my 2s are going to be lined up here. And then when I can't divide by 2, I would try to divide by 3. And then if 3 wouldn't work, I'd use 5. And then I would use 7. And then the goal would be to keep dividing by prime numbers. because the prime numbers are going to be ends of the branches, right? It's the composite ones on the other side that continue to be broken down. So I divide by 2 as many times as I can, and then I would try 3, and then 5, and then 7, and then continue on with those primes until you have a prime number at the very end. And that's just an organizational tool. You can use whatever numbers you want. So like going back to the 50, for example, I started with 2, which gave me the 25. If you didn't want to use 2 and 25, you could have absolutely said, okay, 50 is the same thing as 5 times 10, and then 10 becomes 2 times 5. And you get the same grouping of numbers, a 2 and a 5 and a 5, but now see here my 5s that I have to circle, I have to make this weird like jelly bean type of circle, right? So it doesn't matter how you break it down, you're going to get the same answer. It just helps organizationally to work this way. So that's what you're going to see me do throughout the notes, okay? So to our note sheet, we're trying to simplify radicals today. So what is today, the 26th? When we're simplifying radicals, we want to start by breaking down the radicand. Remember, that's the number and or variable, so we'll get there in a little bit, underneath the radical. So we take our radicand, whatever's under the radical, we break it down. And I like to do this by dividing by prime numbers, although really you can use any number you want. So I start with 2, and then 3, and then 5, and then 7, 11, 13, and then 17, and I don't think you'd really be dividing by anything bigger than that. Usually the 2, 3, 5, 7 is going to kind of get you where you need to be. And you can use whatever factors you want in your factor tree. That's what we're basically doing here, right? And this step is making a factor tree. But organizationally, it's helpful to go in order. Okay, once we have our radicand broken down, we're going to circle groups of numbers that are based on the index. So if we have a square root, we're going to be circling pairs. If we had a cube root, we'd be circling groups of 3. And if it was a fourth root, groups of 4, and so on. And the circled groups represent perfect roots. Okay, circled groups then are perfect roots. That means they can come out of the radical. And the uncircled or ungrouped numbers are not perfect squares. They're going to have to stay inside the radical. And if you have multiple groups that come out, they get multiplied. And similarly, if you have multiple groups that stay in, they get multiplied. Which should make sense. Okay? So, looking at the square root of 18, if you don't have to break this down, if you can look at that and say it's 9 times 2 and I know the square root of 9, if that can happen in your head, awesome. If not, totally okay. So if I was looking at 18 and I wanted to break it down, it's even. 2 goes into it 9 times, and then 9 we can break down to 3 times 3. And since my last branch here is now a prime number, I know I'm done. So 2 times 3, here's a pair of 3s. That pair of 3s again represents the 9 that we had here. That's a perfect square. What's the square root of 9? It's 3. So this pair of 3s tells me 1 3 can come out of the radical, because that pair of 3s is 9 and the square root of 9 is 3. So the pair of 3s tells me 1 3 can come out of the radical. And then left in the radical is anything unpaired, which happens to be the 2. So 3 radical 2. Get rid of this for later. So what you're doing is, again, circled groups. Shows you what comes out of the radical. Anything that's uncircled, unpaired, has to stay in the radical. So our answer here, simplified form of the radical 18 is 3 radical 2. Now if you try to put radical 18 in your calculator, and let me just, darn, I don't have Desmos. Give me a second here. I'm going to pull my Desmos up so you can see. Let me split screen this now. I don't know why I didn't have that ready. My apologies. Again. Don't mind my technology struggle. My goodness. Getting all that? Okay, come on, calculator. There we go. Okay, if you put the square root of 18 in the calculator, so square root of 18, majority of calculators, there are some that might actually simplify this for you. The majority of calculators are going to tell you the decimal form for that number is 4.2. Well, that's not really helpful when you're looking at what's the simplified answer, but you still could use your calculator to verify. So what I'm saying here in the green box is that radical 18 is equivalent to 3 radical 2. That means it's in a simplified form, but it should be equal. So if I type in my simplified form, my 3 radical 2, it better give me the same decimal. So even though the calculator won't break this down for me, I can still use the calculator to verify that those decimal amounts are equivalent. So what I'm saying is equivalent is actually true. Okay? So let me get rid of this. All right, so square root of 135, if we're to break this guy down, this one is not even, which means we can't divide by 2. So the next number I would try to divide by is 3. Now, does 3 go into 135? Or do you know the trick to see if a number is divisible by 3? So we know it's divisible by 2 if it's even. If the sum of the digits is divisible by 3, then our number is divisible by 3. So in this case, if I add 1, 3, and 5, I get 9. And because 9 divides by 3, that means 135 divides by 3. So I'm going to start here with 3. And 3 is going to go in 45 times, which is composite. 3 goes into 45 15 times. And then 15 becomes a 3 times a 5. So I have a pair of 3's here, which represents 9. So that pair of 3's represents 9. Square root of 9 is 3. That pair of 3's tells me a 3 can come out of the radical. And then unpaired this time, we have a 3 and a 5, which means this simplifies into a 3 and a radical 15. So that's the simplified form here. And again, if you put radical 135 and 3 radical 15 both in the calculator, you should get the same approximation for both. All right, now number 3, I threw in a variable. Okay, what's going on with the variables here? Let me take you back to my scratch paper for a second. If we use a property we talked about in the last set of notes with our rational exponents, let's say we're looking at, and I actually think this one was in the notes, let's say we're looking at the square root of x to the, well, let's go cube root of x to the 6th. Remember, we could rewrite this as a rational exponent. We said if we take the exponent and divide by the index, that this would be equivalent to x to the 6 divided by 3, which means it's really the same thing as x squared, right? That's because, or this works out to be a whole number because x squared it's a perfect root. And the same thing if we had, let's say, the square root of x to the 8th, right? We take the 8, we divide by the square root, so that's really x to the 4th. Okay, anytime it's a number that divides evenly by the index, it's going to be a perfect root. Now, on the one we had in the notes, which we're going to come back to, we had something that wasn't exact. So I could divide any even number by a square root. But what if we had something like the square root of x to the 3rd? It's true that that is 3 divided by 2, but that doesn't divide evenly, and I don't want to leave a rational exponent in this simplification. That's an equivalent form, but that doesn't help us simplify. Okay, what we have to do is find the perfect root that's in this radical, and we can do use the same approach we use with the numbers. So x to the 3rd power, if we were to break this down, is really an x times an x times an x, right? That means I have a pair of x's in there. That pair of x's tells me one x can come out of the radical, and this leftover means one x has to stay in, right? Which makes sense. This is an x squared, and that's an x. I can square root the x squared, but I can't square root the x, okay? Now, if it was something larger like x to the 31st, I don't know that I want to write out 31 x's, right, and look for pairs, because ultimately it is just division. If I take the 31 and divide by 2, how many times does 2 go into 31 evenly? Well, it goes in 15 times evenly, and there'd be 1 left over. That means when I simplify this, I'm going to have x to the 15th on the outside of the radical and x to the 1st left in the radical. So you can still use the division. It's just if it doesn't divide evenly, if there's a leftover, that leftover is something that's going to have to stay in the radical. Okay? So let's go back here. If we're looking at 108 x to the 3rd, 108 x to the 3rd under the square root, the number portion of this, same thing. Let's break down the 108. 2 goes into it. Let's see, 54 times, that's even. 2 goes in 27 times, that divides by 3. 3 goes in 9 times, and then 9 becomes 3 times 3. So if it was just 108, I'd be taking out a 2, I'd be taking out a 3, and I would have a 3 left over. But now I also have an x cubed, which means I can also take out an x. So I'm taking out a 2, I'm taking out a 3, I'm taking out an x, and left over in the square root, I have a 3 and an x. which means the final simplified answer here is going to be 6x times the square root of 3x. Now you can verify the 6 radical 3 part with the calculator, but the calculator is not going to be able to handle the variable part. Okay? Hopefully that made sense. All right, let's look at a cube root. No variables, but just a cube root. We're still going to break down this number. 2 goes into 40 20 times. 20 we could say is 2 times 10. And then 10 we could say is 2 times 5. Now since it's a cube root, we would need a group of 3 in order for it to make a perfect cube, right? 2 times 2 is 4 times another 2 is 8. And 8 is a perfect cube. What's the cube root of 8? It's 2. So now this group of 3 2's tells me that a 2 can come out of this radical. Now you got to be really careful here because there's already a 2 on the outside of the radical. Change colors here. And the 2 that's already on the outside, that coefficient, that means take whatever you're doing and multiply by 2, right? So if I have a 2 that's already on the outside, it's going to stay there. And now because I grouped up this grouping of 2's, I can bring out another 2, right? That's coming out. And then left over in the cube root, we have a 5. So the 5 is coming here. All right, lots of arrows. I apologize if that's looking ugly on your own paper, okay? But the final simplified form here. So we had a 2 that was already outside, brought in another 2 to make the 4, and then left over in the cube root, we had a 5. So 4 cube root of 5. And again, no variables. If you put the original problem, the new simplified form in the calculator, it's going to verify that those two decimal amounts are the same. All right? Got a negative 81 here. What happens with the cube root of a negative? Do you remember? Cube root of a negative is just going to be negative. So that negative is not really going to affect what we're doing. But we can take the cube root of negative 1, so that's going to just make our answer negative, right? Let's break down this 81 first. Not even, but 3 goes into it. 3 goes in 27 times. And then 27 is 3 times 9. And then 9 is 3 times 3. So a group of 3. There we have it. And if we have an x to the 5th in there, that's 1, 2, 3, 4, 5 x's. And since it's a cube root, we're looking for a group of 3's. We have one. So from this radical, the negative, cube root of a negative just becomes a negative. So this makes our answer negative. That negative basically just can come out. And then we circled a group of 3's here, so a 3 can come out. And then we circled a group of x's, so an x can come out. And then left over in our cube root, we have a 3, and we have 2 more x's. A 3 and an x and an x. So this answer becomes a negative 3x in front of a cube root. That's too squished. Let me write this here. We have a negative 3x in front of a cube root of 3x squared underneath our radical. Okay? All right. Feel free at any point to pause and try a problem out on your own. I don't think I've labeled any U tries here, but by all means, you could try to work this one out and then come back and see how you did. 343 is obviously not even. Not going to be divisible by 3 or 5, but 7 goes in, and 7 goes in 49 times, and then 49 becomes 7 times 7. So I'm going to have a group of 7's that come out, and notice there's nothing left over. What does that mean about the cube root of 343? It means it's exactly 7, right? If there's nothing left over, there's nothing to go inside of a radical, it's a perfect root. That's what would happen if we were to break down, let's say, a square root of 25, right? Square root of 25 we know is just 5, but if you were to break it down, a pair of 5's would come out and there would be nothing left over. So we've got that, and then we also have x to the 6th, right? 1, 2, 3, 4, 5, 6 x's. 2 groups of those can come out, and again, nothing left over. That's because 6 divides evenly by 3. So this is going to be exactly 7x squared with nothing left over in a cube root, so no more need for a radical. Okay? That's actually one that I probably wouldn't have broken down. That'd be like if I said, what's the square root of 49x squared? This is something you shouldn't have to break down because you know the square root of 49 is 7. And if I take the 2 here and divide evenly by the 2 here, I get x to the 1st exactly. Okay, same kind of concept. So if you recognize you have perfect roots in there, then you don't need to do that breakdown. Totally fine to skip that. Okay, same process here, but now we have a 4th root. So a 4th root now means we're looking for a group of 4 factors. So if we were to break down 32, 2 goes in 16 times. 16 becomes 2 times 8. 8 becomes 2 times 4, and 4 becomes 2 times 2. So I've got a group of 4 2's, and then I've got a 2 left over. And then 9 x's means I have 2 groups of 4 and 1 left over. So 2 groups of 4 and 1 left over. So I have a negative on the outside that's got to stay there. I'm bringing out a 2. I'm bringing out 2 x's, which is an x squared. And then left over in my fourth root, I have a 2 and I have an x. And that would be the simplification for that radical. Okay? Again, feel free to pause at any time if you want to try this next one. Fifth root, so now we're going to break down and look for a group of 5. So we have an even number. 2 is going to go in 105 times, and that's not even, but 3 goes in. 3 goes in, 35 times? And then 35 we can break down to 5 and 7. So no pairs, right? No pairs, no groups of 5. Can't take out a group of anything there. And then if I have an x to the fourth, I can't get a group of 5 x's either. So this is almost the opposite of what we had going on in number 6. In number 6, we had everything grouped up and nothing left over, so no radical left over. So everything came out. Here we have nothing to group up. That means nothing can come out. That means everything stays in. So if everything stays in, then our answer and our problem were the same. All right? That means that this radical is already in simplified form. It'd be like if I said simplify a square root of 2. Well, there isn't anything else I could do to simplify a square root of 2. That would be the answer. Or if I said reduce the fraction a half. Well, I can't. 1/2 is as reduced as that fraction gets. All right, so if you break everything down and you don't have any groups, that means you can't simplify any further. Your answer is as simplified as it gets. Okay? Got one more here to try out. That's another square root. Back to the basics here. So we're going to break this down to 2. And how many times does 2 go in? 64 times. Now, just so you can save yourself a little bit work smarter, not harder. If I was doing this problem, now that I see my perfect square of 64 there, I would stop. What's the square root of 64? It's going to be 8, right? So I already know an 8 is going to come out of this radical and a 2 is going to stay in. And then I deal with the variables, where if you took 5 and divided by the index of 2, 2 is going to go into 5 twice, and there's going to be 1 left over. So if you can do the answer, or do the problem, that quickly and work most of that out in your head, then by all means. But if that's not where you're at, that's totally okay. So if you wanted to break this down all the way, 2 goes into 64 times, 2 goes into that 32 times, that's 2 times 16, that's 2 times 8, that's 2 times 4, and then 2 times 2. Square root. So we're looking for groups of 2. There's 1, there's another, and there's our leftover. And then if I have 5 x's, then I got 2 groups of those to come out. So I'd be taking out a 2, another 2, another 2, an x, and left over, I'd have a 2 and an x, which would make this an 8x squared in front of a square root of 2x, which is the same thing I showed you a moment ago, just a much longer way to get to that answer. But this doesn't have to be about working fast. So whatever option is going to be good for you, you take that option. Okay? So that's simplifying radicals. If we can simplify, that's the harder part of the multiplying and dividing. The multiplying, why do I have this twice? What in the... Okay, I'm not sure what's happening with my notes here. Okay, so there's page 1. Let's go to page 2. We're multiplying radicals. I'm sorry for all that scrolling. So multiplying it's really the reverse of what we just saw. So when we looked at the square root of 50, I said, well, let's break that into 2 separate radicals, right? The 25 and the 2. And what we're looking at here is the reverse. You're going to be possibly starting with 2 separated radicals. The goal would be to put them back together to 1 and then simplify the 1. Okay? So we're basically using the same property that we saw a few minutes ago in reverse. As long as your radicals have the same index, you can multiply them. So we have a property. This is the reverse of what we saw on the front there. It says if we have the nth root of a times the nth root of b is the nth root of their product. So we're going to try to multiply to make one radical and then simplify the one radical. Okay, now when you're multiplying, if we throw some variables in there, which you can see them in 12, and then I should label a huge try there. You're going to apply your product rule. So we multiply coefficients, and then if we have any variables in there, what happens to the variables? The exponents on the variables get added. So multiply and add. Okay, add the exponents for the like basis. So looking at number 10, I know we could simplify the radical 18, but in these cases, it makes more sense to multiply and then simplify versus simplify, multiply, and then simplify again. So I'm going to multiply the 3 and the 18 to make this one radical of 18 times 3 is going to give us 54. So now it's just one radical to simplify. If I break down the 54, it's 2 times 27. 27 is 3 times 9. And 9 is 3 times 3. It's a square root, so I need a pair, and I have that. It means a 3 can come out of this radical, and if a 2 and a 3 stay in, that's going to give me a 6. So this simplifies to 3 radical 6. Okay? Same thing here, except now you notice we have coefficients of our radicals. So when I multiply here, the coefficients get multiplied to give us a new coefficient. So 2 times 4 on the outside gives us 8. And then the radicans get multiplied to give us a new radican. So 5 times 8 gives us 40. So now we have one radical, and we simplify the one radical. So 40 is 2 times 20. 20 is 2 times 10. 10 is 2 times 5. That means I could take a 2 out. Now I'm taking a 2 out, but there's already an 8 out there. So what happens with that 2 and that 8 is we multiply. So we have a 16 on the outside of the radical. And then left inside is a 2 and a 5, which gives us a 10. So 16 radical 10. And just like I showed you a few minutes ago with the calculator, if you put this original problem in and you put the 16 radical 10 in, it's going to show you that the decimal values are the same so that you can verify that those two amounts are actually equivalent. Okay? Now if we throw variables in, same process, it just looks a little uglier. So we want to multiply to make one radical. We're going to make this one radical of 6 times 2 is 12. X to the 2 plus the 1 there gives us an x to the third. And then y to the 3 plus 4 makes 7. So now we simplify. 2 times 6 that we just saw. 6 is 2 times 3. That means we can take a 2 out of this. If I've got 3 x's, I can take one of those out as well. And if I have 1, 2, 3, 4, 5, 6, 7 y's, I can take 3 of those out. So this becomes a 2, an x, a y cubed, 3 y's come out, and then left over in the square root is a 3 and an x. And that's our simplification. Okay, now I'm going to move right along to the next one. Again, feel free to pause the video and try it out on your own. So we're going to make this 1 cube root of 9 times 3 is 27. X to the 1 plus 2 is 3, and y to the 4 plus 2 is 6. Now, I'm hoping you're looking at this and recognizing that these are all perfect roots. We should know the cube root of 27. What's the cube root of 27? It is 3. And then 3 divides evenly by 3. What's 3 divided by 3? 1. And then 6 divides evenly by 3. What's 6 divided by 3? It's 2. So this is going to be exactly 3xy squared. Now, if you don't see it, it's okay. You can still break it down and get to the same answer, but these are hopefully things you're recognizing. So 27, again, 3 times 9 and 3 times 3. There's your 3 that comes out with nothing left over. 3 x's, that comes out, nothing left over. And then 6 y's, right? 2 of those come out, nothing left over. So this is going to be exactly, again, 3xy squared with nothing left in the radical because this was a perfect root. So exactly 3xy squared. Okay? And division works the same as multiplication most of the time. If your radicals have the same index, again, you can divide to make one radical, or you can separate, and I'll show you that when we get to the back. So the nth root of a divided by the nth root of b is the same as the nth root of a divided by b. So the goal here is going to be to divide to make one radical, and then we're going to simplify the one radical. And again, we might have to apply our quotient rule when we throw some variables in. So with the quotient rule, we divide coefficients and subtract exponents. So we use our divide rule or divide and subtract rule. All right, so here, we divide the coefficients, new coefficients of 9, And we divide the radicans. 72 divided by 3 is going to be, what, 24? So we divide to make one radical and then simplify the one radical. So 24 is 2 and 12. That's 2 and 6. And then 2 and 3. So a 2 is going to come out. Now I already had a 9 out there. When I multiply by the 2 that I'm bringing out, I end up with a negative 18. And then a square root of the 2 and 3 left over gives me a 6. So negative 18 radical 6 is our simplified answer there. Okay, here we're going to divide to make one cube root. 48 divided by 2 is going to be 24. And then we have x to the 5 minus 1 is 4. And then y to the, be really careful with your signs here. This is 1, and we want to subtract a negative 2. So that's going to be a 1 plus 2, which makes this exponent of 3. So 24, again, we get to break down, is 2 and 12. That's 2 and 6, and 2 and 3. So the breakdown's the same, but this time it's a cube root. So I'm going to be able to take out a 2, and there's only going to be a 3 left over. And if I have 4 x's, I could take one of those out as well. If I have 3 y's, one of those comes out too. So this is going to be a 2, an x, and a y in front of a cube root of 3 and x is what we have left over. Okay, so if you're ready, pause the video, give this next one a try. We're going to divide to make one square root of 120 divided by 2. It's going to give us a 60. And then 1 minus 1 is 0. Those x's are going to cancel, so they're gone. And then we have y to the 5 minus 1, which is 4. So 60 is 2 and 30. That becomes 2 and 15. That becomes 3 and 5. And so a 2 is going to come out. And then if I have 4 y's, then 2 of those come out as well. So this is going to end up being a 2y squared. And in front of a square root of 3 and 5 makes 15. So 2y squared, square root of 15 is our simplified radical. Okay? Now, most of our multiplication division will be pretty straightforward. Sometimes our division, not so straightforward, and that's what we have happening here. Okay? A process we call rationalizing the denominator. So if you look at number 15, for instance, this is still a division problem. The issue is I can't divide, right? I can't divide 5 into 2 to make that one radical. Now, I could rewrite it as a radical 2 over 5, but I don't know if that's helpful in any way, okay? Still can't divide the 2/5. But we have this unwritten rule in math, and it's something that will be helpful when you get to the, let's say, calculus level. At this point in our math careers, it's kind of a trivial thing. It's more just about working with algebra. But we're not allowed to leave irrational numbers in the bottom of the fraction, irrational numbers like a radical 5. We want to try to simplify this so that it's a number that's a little more comprehensible. Which again, when you get to calculus, this will make a little more sense. But what could we do to this fraction to try to simplify? Well, I can only do things to the fraction that aren't going to change the value of the fraction. For example, multiply by 1, right? If I multiply the fraction by 1, it doesn't change its value. So that's the take I'm going to use here, multiplying by 1, but we're going to use a special form of 1. In this case, what we're going to do is we're going to multiply by a square root of 5 over square root of 5. So square root of 5 over square root of 5 is 1. Again, I'm multiplying by 1, not changing the value of the fraction, but this works out nicely here because on the bottom, what is the square root of 25 times the square root, or square root of 5 times the square root of 5? Well, it's the square root of 25. And what's the square root of 25? It's exactly 5, which was the goal, to get a rational number in the bottom of the fraction instead of the irrational. Now on the top, the 2 times the 5 gives us a radical 10, and that can't be simplified, but that's okay. The irrational in the numerator of the fraction is preferred to it being in the denominator. Okay, so radical 10 over 5 is going to be the simplified form of that fraction. So we call this process rationalizing the denominator. When the denominator of a fraction contains a radical that can't actually divide into the numerator, we rationalize it. And we rationalize by multiplying by 1, right? Multiplying by 1 so that we don't change the value of the fraction. But specifically, we're going to multiply our top and bottom, our numerator and denominator. I don't want to be too lengthy with the words here. The numerator and denominator, the top and the bottom, by a radical that makes a perfect root. Right? The goal is to get a perfect root on the bottom. So that's why I multiplied by radical 5, because 5 squared gives us 25, which is a perfect root. And once we simplify, we should have a rational number in the bottom. And that's the goal, okay? So looking at number 16, we've trying to multiply. I can't divide, right? 18 can't go into 5. And I know that we can simplify the 18, but I don't want to have to simplify in the beginning and then possibly again in the end. So we're going to save all the simplifying of radicals till the very end if that's going to be necessary. So the goal here is to multiply by something that makes a perfect root. Now I could absolutely do the same thing I used in the last one. I could multiply by another radical 18 and radical 18, because if I square a number, it's going to make a perfect square, right? But if we can use a smaller number is going to be easier for us to work with here. Now, any number that I multiply by, as long as it makes a perfect square, we're going to be in good shape. So think about your perfect squares, right? Perfect squares would be 1 and 4 and 9 and 16 and 25 and 36, and I could keep going with that list, but as soon as I recognize that 18 is a multiple of one of those, I know exactly where I'm going, right? If I multiply 18 times 2, or radical 18 times radical 2, I'm going to get radical 36, which is a perfect square. So instead of using radical 18 and 18, which would absolutely work, as long as I can multiply by something that makes a perfect square, I'm good. So I'm going to use a radical, I guess I should turn the pen on, a radical 2, now it looks ugly, try that again. Radical 2 over radical 2. So on the top of the fraction, radical 2 and radical 5 makes radical 10 again. On the bottom, radical 2 and radical 18 gives us radical 36. But what's the square root of 36? Is 6. So radical 10 over 6 is going to be our simplified answer. And again, if you put the original problem in the calculator and put the new one in the calculator, it will verify that their decimal amounts are the same. Okay? All right, how about here? So radical 3/7, again, this is not something that we can divide, and just so it looks a little more like the other two, I could say this is the same as radical 3 over radical 7. What can I multiply by to fix this? Well, I can multiply by a radical 7, because what's radical 7 times radical 7? It's radical 49. But what's the square root of 49? It's back to 7, okay? On the top of the fraction, again, that was 7 times 7 to make the 49 on the top. 3 times 7 makes radical 21, and that can't be simplified. So radical 21 over 7 is going to be our answer, okay? So feel free to pause if you want to try this one out. I'm going to keep working here. So thinking about perfect squares again, I can make this one a 16 if I multiply by a radical 2. Radical 2, radical 2. So that means 2 radical 2's on the top. And on the bottom, 8 times 2 makes 16. So I get 2 radical 2 here, and then 2 radical 16 on the bottom is going to give me a 4. Now this one's actually not done, because outside of the radical here and here, we have numbers that are reducible. They have something in common. So I can reduce this by dividing by 2. So this gets reduced by a factor of 2 on the top and the bottom. So final answer, let me get rid of this. If I reduce by 2 here, 2 goes in here once and it goes in here twice. So I end up with, on the top of the fraction, 1 in front of my radical 2, and on the bottom, just a 2. So radical 2 over 2 is going to be that simplification. Okay? I hope I'm not going too fast. All right, here we go. Now we've got a cube root on the bottom. Okay, cube roots are going to be a little bit trickier, but I'm still trying to use the same concept where I'm multiplying by something that's going to make a perfect root. The question is, what am I going to multiply by, right? Now think about your perfect cubes. Perfect cubes are 1, and then 2 cubed is 8, and then 3 cubed is 27, right? The goal is to make this number one of these perfect cubes by multiplying it by something. Well, I could definitely make the 2 and 8 by multiplying by 4, right? So the goal here is going to be put to multiply by a cube root of 4 and a cube root of 4. So that on the top of the fraction, we have 1 times a cube root of 4, which is just 1 cube root of 4. And on the bottom, we have the cube root of 2 times the cube root of 4, which gives us the cube root of 8. But what's the cube root of 8? It's 2. So we have a cube root of 4 over 2. Okay? Similarly here, and maybe we can kind of see what's happening, right? So if you think about our cubes, 1 and then 2 cubed is 8, 27, 4 cubed is 64, 5 cubed is 125, 6 cubes, 216, 7 cubes, 343. That's going to be the goal here, which hopefully you saw that, because what is this 49 really? Right? It's 7 times 7. If I want a perfect cube, how many 7s would have had to been in there for it to be perfect? Well, it would have had to been 3 7s, right? And the 3 7s would have given us the 343. So I know if I multiply this one by a cube root of 7 and a cube root of 7, I'm going to get those 3 7s, or that 343. Okay? So a cube root of 7 and a cube root of 7 is going to give me cube root of, on the top, 5 times 7 is 35. And on the bottom, it's the cube root of 343. Excuse me. But what's the cube root of 343? Again, is 7. So cube root of 35 over 7 is that simplification. Okay? Getting there. So it's a cube root now of 5x. So perfect cubes, hopefully you're seeing, I could make this a 125 if I multiply by, right now I need 3 5s to be in there. If there's only 1 5 in there, if I multiply by 2 more, or 25, right, multiply 5 times 25, I'm going to get to that 125 that I need. So multiplying by cube root and a cube root, excuse me, I'm so sorry, of 25, I know is going to get me from 5 and 25 to the 125. But what about the x? Okay, well, x to the first is no good under a cube root. It won't be able to come out. Altogether, what would I have to have under the cube root to be able to divide evenly? Well, I'd have to have an x to the third there, right? So if I've only got one x, I would have to multiply by 2 more x's to give me those 3 all together. So if I multiply by a 25x squared and a 25x squared, then on the top, I get 6 cube root of 25x squared. But on the bottom, I now have the cube root of 5 times 25 is 125, and x to the first and x squared is x cubed. But what is the cube root of 125x cubed? Well, it's going to be 5x. So 6 cube root of 25x squared over 5x. Okay? That's about as difficult as you may see here. Again, feel free to pause if you want to try this one out, but I'm going to continue to work here. I'm going to have to multiply by a square root and a square root. Well, this isn't so bad. If I multiply by 3, 3 times 3 will give me a 9, which is a perfect square, and then an x, right? And x times an x will give me an x squared, and that's a perfect square. So a 3x on the top and the bottom. It's going to give me, let me write my equal sign 3 times. It's going to give me 4 times square root of 3x, so 4 square root of 3x on the top. And on the bottom, it's the square root of 9x squared. So what's the square root of 9x squared? It's just a 3 and an x. So 4 square root of 3x over 3x is our simplified radical. Okay? So I know I went kind of quickly. Feel free to pause, and then again, email me if you have questions. I can try to do some further explanation for you and make sure you're getting in there to Math Lab to work on your assignments, which are all going to be due